Sub year 12. Okay, guys, we're continuing with mass spec. I'm gonna rattle on. Let's crack on. Share screen. Go, 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 go. Get rid of this. Laptop is really struggling at the minute. Okay, straight back in. Right, this is where we left off. Amazing. Go, 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 go. Oh no! Oh no! I need to pause it. Go. It is really, really struggling. It's really struggling. I'm not entirely sure how to fix that. Oh, can I turn down the settings on this? I'm receiving you guys. Video, receive. Can I turn it down even less? Audio won't. No, that doesn't help. Damn. Ah, man. Okay, camera. Fine. Okay. 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 Right, everyone should be able to see me. Can you guys give me a quick thumbs up if you can see me? And that the screen's working all right and you can see my screen. Have I shared it? I hope so. Right. Excellent. All right. Okay, guys. Laptop is really struggling. I probably need to restart the thing. It's been a while. Okay. So title is atomic structure. I think this is lesson 5 now, but this is mass spec. Ooh, that's thick. Let's turn that down a bit. I haven't actually got my learning objectives up. I usually do. Mass spec. Mass spec. Diatomics. Oh, I'm just going to put mass spec of molecules. Mass spec molecules. Okay, so learning objectives. First thing is understand. Oh, these are actually on my YouTube channel, I believe. I'm sure they are. Understand diatomic mass spec data. So this is, and I'm going to focus, you must know 2 people. Chlorine and bromine, and then be able to apply your understanding to all the others. Next is I need you guys to understand fragmentation. Fragmentation of molecules. And then be able to identify MR from graphical mass spec. Graphical MS data. I like it. 3 learning objectives today. Okay, so last lesson, we were putting elements into the mass spec device, but they were not the diatomics. We were mostly looking at metals, is what we were focusing on, and now we're going to start looking at the diatomics. Now, we know our diatomics. First thing I think we should probably do is remind ourselves of the diatomics. So diatomic elements, we know these. Yeah, and it is any element ending in "-ine", or "-gen". So for example, let's list them. There are 7 diatomics. Hydrogen. Yeah, I'm just gonna hydrogen. Then we have nitrogen. And then we have oxygen. And then we have fluorine. Fluorine, chlorine. And then we have bromine. And iodine. 7 elements travel around in pairs. Now, we can actually argue, at this point, I've always got a year 10 student who's been a pain, who's like, yeah, but there's always astatine as well. And he is right. Astatine is astatine. Astatine is in group 7 as well, and that will also be diatomic, AT2. But the thing is, we never deal with her. We never deal with her because she actually has a Guinness Book of World Records. She is the least abundant. Has a world record for being the element with the least amount of it on the entire planet. There are 2 grams of astatine on the entire planet, and they're actually being made and destroyed in the planet's core all the time. This is because it's radioactive, so we never talk about astatine, so we can just ignore her. Never mention her in an exam, unless they mention her. Okay, So we know our diatomics. Let's do formulae. N2H2O2, F2, Cl2, Br2, and I2. We'll have to do an entire topic on group 7. This is group 7. Group 7 are important, and you've got to know these guys. You did them at GCSE as well, but always nice to just remind you that these are important elements. So we know our diatomics. I'm just going to add a nota bene at this point. Nota bene, change your color to red. I think it's that one. Yeah, nota bene. The nota bene is there are other elements that travel in groups. So the nota bene, sulfur travels as S8. Yeah, but the only time you ever use this, only used in bonding questions. In an equation, you just put it in as S. The reason being is S8 is such a big number, it's going to make the equation way too large, so they just don't bother. But for bonding, you need to know that sulfur travels around in 8s. It's really easy to remember because you can just do sulfur with a little baby S and then just finish it. Isn't that cool? The other element is phosphorus. Phosphorus, now this one you do always have to use, is P4. Yeah, phosphorus is in fours. Yeah, I like it. It's good to know those people. Okay. So, the diatomics. So what we're now going to do is, we're now going to focus on 2 in particular. So, go back to my notes. So we can put mass spec of chlorine, of Cl2 gas. Now, the great thing is we don't even need to use the vaporization chamber in this particular setting because chlorine is already gas, which is amazing. So she just gets shoved straight into the ionization chamber. So when you put chlorine into the ionization chamber, and here's the picture. Yeah, we put chlorine. Well, I didn't do that very well, did I? That's better. There's chlorine. So chlorine travels around in pairs. You remember these dot and cross diagrams? Yeah, so here's chlorine traveling around in pairs. Now, we know from our previous lessons, we know that chlorine exists in 2 versions. Chlorine 35 in a ratio of 3 to chlorine 37 in a ratio of 1. So we know there's 2 versions of chlorine. Now, when we put chlorine into the mass spec device, the first thing that it goes through is ionization. And we're going to fire from an electron gun. So electron gun, 1 mark. High energy electrons, 1 mark. Knocks off, it's with a K. Made a mess of that. Knocks off outermost electron. Yeah, forming positive ions. Right, let's look what this looks like for chlorine. So here goes in my high energy electron. It's going to hit the chlorine. And the problem is we're going to knock off one of these electrons. Now, what we're going to do is I'm going to pick someone. So what I'm going to do is I'm just going to go pick. I'm going to change my pen color to red. And I'm going to say Anch. So electron 1, 2, 3, 4, 5, 6, 7, and 8. Anch, which electron would you like me to knock off out of those 8? Give me a number. Use your hands if you like, Anch. Use your hands, your fingers. Number 4, I like it. So Anch has just hit number 4. And he's going to knock off that electron. So look what this now becomes. This now becomes this picture. Damn it. Laptop's just not as quick as I do. I hate the fact that it's got bigger. Hate the fact that it's still got bigger. I don't know why this is doing this. It's just really struggling. I knew that it was going to get really tricky. Guys, you know what I'm going to do is, can I ask you guys to just, let's end the Google Meet. Let's just get rid of the Google Meet. I just think I'm just going to get rid of the Google Meet. I know you guys are there. I'm going to end it. Right, let's get rid of that. Okay, so it's going to be very interesting to see what difference this makes to my little computer. A massive difference. Okay, so this is what we've now just made. We've now made chlorine molecule, and now one electron is now missing. So I have now made, thanks to Anch, this guy. And the whole thing is in brackets +1, and I've got 2 electrons spat out, because one of them was the high energy electron, and the other was the electron I had. The equation, of course, was this, yeah, the electron from the electron gun, and then 2 electrons spat out. Now, if this was the case, now Anch chose electron number 4. Now, if this was the case, it means that in my mass spec data, I'm going to get a peak. So this is M over Z, and this is abundance. Okay, so we now get a peak. Now, the question is, who were the 2 elements that were joined together? Now, what options did I have here? I could have had, let's look at our options. We could have had chlorine 35 bonded to chlorine 35 +1. And I'm going to see a peak there at 70. That peak, if I saw it, would be at 70. But there was another option. I could have had chlorine 35 hitting with and joined to chlorine 37 +1. That would have given me a peak at 72. That would have given me a peak at 72. This is where I need to move my numbers over. This is 70. This is 72. I had another option. I could have also had chlorine 37 bonded to chlorine 35. Now, the great thing is these 2 are the same. So these guys are the same, so it makes no difference. But I'm going to come back to that later. But there is another option. I could have had chlorine 37 and chlorine 37. Now, this one's going to be the rarity. Yeah, because these guys give the same peak at 72. This one gives a peak at 70, and this one gives a peak at 74. Now, the peak at 74, what you'll notice is the peak at 74 is the smallest. And this is kind of common sense. I have the least amount of 71 in my mix. It's only 1 in 4. So the chances of me having 2 37s joined together is going to be relatively slim. Now, you'll notice that I've given them particular heights. I'm going to explain that height to you momentarily. Okay. Now, these peaks here are called parent peaks. These are called parent ions, or sometimes referred to as molecular ions. Same thing, just the ions of the molecules. Now, the reason why they're called parent and molecular ions is because the molecule made it through without breaking. So what we now realize is, depending on which electron you hit, may change this process. So if we put in chlorine, I'm wondering, I'm going to ask this on the chat now, on the YouTube chat. No one's commented yet. I'd like you guys to have a go at this. So on the YouTube chat, please, can you type in the number of the electrons in that image that are, if I knock it off, will cause the molecule to break in half? Okay, so this process, so when molecules are put into mass spec machines, the ionization process can cause the molecule to fragment. Notice my capitalization. Fragment. So fragment, this process, the process is called fragmentation. Fragmentation. Now, I've had nobody yet contribute on the chat, which is a little bit upsetting. Can someone just comment on the chat just to make sure it's working? I feel like it might not be. So I asked you guys which electron would be knocked off that may cause the molecule to split. 1 and 8. Well done, Harry. Good man. If we were to knock off electrons 1 and 8, yeah, 1 and 8, thank you, Louis, thank you, Yihan. If I knock off 1 and 8, then I'm going to halve the strength of that covalent bond. What that means is the molecule is now going to go through fragmentation. Let's look at the image. It's going to do this. I had chlorine here and here, had electrons on this guy, and now I'm going to knock off that circle at the top, right? So the whole thing now becomes positive, but this covalent bond has just halved in strength. Now what that means is it's going to split. So it's going to split into 2 particles. It's going to split into 2 particles. But the particles are going to be subtly different. Now, what I'm going to show you is this one. I'm going to choose this. There you go. Now, when this happens, something very cool happens. The electron, this electron here that was still left, this electron there, that's going to go with either him. It's either going to go with him or him. It's actually 50-50. The fact that it was owned by the Cl on the left primarily didn't make any difference. The ownership is the same. It's going to just rip it off and go in either direction. But when I do this, what now happens is one of the particles will become fully positive and the other becomes electrically neutral. So if I write this as an equation, it becomes Cl2 plus can become Cl plus and Cl. This one, by the way, sorry, I'll keep that the same as what it is on the other side. So what's happened is I've produced this is a chlorine atom. It's just a chlorine atom. It was the original atom. It owns its own electrons, so it's uncharged. But this is now a chlorine ion, a chlorine positive ion. It's not a chloride because it's not negative. It's a chloride cation. Yeah. Now at this point, because it splits in half, I can only detect the positive cation. This guy is lost in the machine. It's actually removed by the vacuum pump, but it's just lost in the machine. The positive ion is what now gets accelerated. Now what that means is I'm going to get 2 more peaks. I'm going to get a peak down here at 35, a peak here at 35, and I'm going to get a peak here at 37. And guess what the heights are going to be of these peaks? It's a bit too long. Guess what the heights of these 2 peaks are going to be? They're going to be 3 to 1. So in reality, if I actually want to do this properly, it's actually going to look like this. This is actually what it's going to look like that. It's a 3 to 1 ratio. Because these are the fragments that I'm detecting. I'm detecting the pieces. Now, it's just purely chance. But the great thing is because there are so many ions, because we have Avogadro's number of particles in 1 mole, you know, this is in times 10 to the 23, you're always going to have enough particles to see an even split in the data. It's the beauty of statistics. So the question is now, what are the ratios of the molecular peaks? And we can now work this out. Okay, so let's have a look. Now I stole this method. The great thing is you only need to be able to do this for the diatomics. You don't need to go further than this. What that meant was I stole a neat trick. See, I used to teach A-level biology and GCSE biology as well, but I used to tell, and one of the things I stole from them for chemistry was a Punnett square. So we know that chlorine is joined to chlorine in a pair. Now, when we see the fragment pieces, 35 and 37 in a 3 to 1, yeah, what we're seeing here is the single atoms. Now that was chlorine 35 plus 1, and this peak was chlorine 37 plus 1. I'm just going to get rid of those numbers there. Cool. It's a 3 to 1 ratio. 3 to 1. So these are the species. These species causing peaks. You can't have whenever this is a really common question at A-level. Give the species responsible for this peak, and everyone gets it wrong because they forget to put the charge on it. Without the charge, you can't detect it, you can't accelerate it, you can't do anything. When you can't deflect it, you can't do anything. If it's not ionized, you cannot accelerate, you cannot deflect, you cannot detect. So you don't forget that charge. Emphasis. Don't forget that charge on your species. Okay, so what's going to happen on the other side? Right, so Punnett square. So I've got two options here. I've got atom A. Let's call this atom A. Now, atom A could be, and it has a 3-to-1 chance of being 35 and 37. So I can go A could be 35, 35, 35, or 37 in a 3-to-1 ratio. Atom B in this, atom B could also be 35 and 37 in a 3-to-1 ratio. So this is atom B. So this is 35, 35, 35, and 37. Now what I can do is I can work out the ratios that these are going to exist in. So if I have, this is where I switch to a different color. So this one's going to produce 70. This pair is going to produce 70, if you're wondering. Yeah, 70, 70, 70, 72. Right, get rid of all those lines. Now that you understand what I'm doing. Yeah. Next, I've got 70, 70, 70, and 72. I have 70, 70, 70, 72. 72, 72, 72, and 74. My ratio of these is 9 to 6 to 1. So I'm going to see my molecular ion peaks in a ratio, I'll switch to black, of 9 at 72, no, at 70. I'm going to see 9 to 6 at 72, and 1 at 74. So it's quite nice to see that a very basic biology trick, 70, 72, and 74. You need, now by the way, I would recommend for you guys to learn those numbers for chlorine. They come up year after year after year and students don't learn them. And they love them. You can work it out using your clever. By the way, anybody here who's a genius at maths can do it using probability. Can be done. But I prefer my method, is just easier. Okay. Now let's look at another element in this scenario. Let's look at bromine. So the title now is bromine. That was a terrible B, wasn't it? Bromine, I hate bromine. Most scary element on the table. Bromine liquid, terrifying stuff. Br2 liquid. So we'll have to put this as a liquid into the mass spec device, into the vaporization chamber. We're going to boil it, going to evaporate it. We're going to boil it, turn it into vapor. This is done in the vaporization chamber. Vaporization chamber. If you're not a gas, you can't be ionized. You can't be ionized if you're not a gas. The reason being is if you fire high energy electrons at a liquid, the energy of the electrons goes into breaking the bonds that are holding it together as a liquid, which means the energy of the electrons goes into turning it into a gas. You don't remove the electrons, so you have to be a gas. Okay, so bromine's now a gas. What we're now going to do is we look at bromine's isotopes. Bromine exists as two versions, bromine 79 and bromine 81. Now we know that bromine exists in a 50-50 ratio. So if I now put bromine gas into the mass spec device, what am I going to see? I'm going to see, number one, I'm going to see a peak at 79. Yeah, I'm going to see a peak at 79. And I'm also going to see a peak at 81. And they're going to have the same heights. Yeah, they're going to have the same heights because they're in a 1-to-1 ratio, 50-50. Yeah. But then what am I going to get for my 3 molecular ion peaks? Now, guys, what I'd like you to do, please, I'd like you to pause the video at this stage and have a go at using the Punnett square. See if you understood what I was doing. Once you've come up with your peaks and your ratio, unpause the video and check to see what I got. Okay, so bromine, atom number 1, Bra, let's call this one A, and bonded to bromine B. Now, bromine A could be Br79, or it could be Br81 in a 50-50. So I can create a Punnett square. So this is atom A, and it could be 79 or 81 in a 50-50. So I only need 2 particles there. The other guy is exactly the same. Br79 and Br81 in a 1-to-1. Right, so this is atom B, 79 and 81. Right, what options am I going to get? So I'm going to get 79 and 79. Well, that's going to be 158. Next, if I go 79 and 81, I get 160. If I now go 79 and 81 down here, I get 160. Then I get 81 and 81, and I get 162. So I have 158, 2 160s, and 162. I'm going to see this, double the height, and that. And this is going to be at 158, 160, and 162 in a 1-to-2-to-1 ratio. Clever game, huh? Can be done. Really, really nice. Now, these are the only two that you're expected to learn. Now, as I said, if you know your abundances, you can work them out, but it does speed up in terms of time-wise when these questions do get asked, because you can predict and you kind of know what to expect. You don't need to show you're working out, you're just drawing the graphs. What we now need to do is to do another question, which is the kind of things that they'll do, where they'll give you someone you don't know, and you're just expected to be able to build a Punnett square from it and create the graph. As I said, you can do this purely mathematically if you want it. Can be done, but it's not easy. Anyway, let's go to the next one. Let's go fluorine. Yeah, fluorine. So fluorine, F2. Now they're going to tell you in the question. Yeah, that's what they will do. So they would say fluorine, so this is the exam question now. Fluorine is found to exist in a sample as 2 isotopes. Those 2 isotopes are fluorine 19 and fluorine 21. They'll tell you their abundances. The abundance ratio is 2-to-1, respectively. Right, so what we know is that F19 is 2 and F21 is 1. It's then going to say, on the graph, draw the peaks that you would see in its mass spec. So, abundance, M over Z. Okay, so what we now know we're going to get. Again, can you please pause the video, have a go at creating it. This would usually in an exam be 4 or 5 marks, I believe. Let's say 4 marks, so 4 minutes. Pause the video, have a go at drawing them. So the first thing we're going to see is we're going to see a peak at 19. That's going to be 2. And we're going to see a peak at 21 of half the height. And it needs to be exactly, that needs to be measured. Yep, half the height at 21. Ratio 1. So you get 1 mark for those two being in their correct ratios. Next, you're going to get 3 other peaks. You're going to get, right, 2 atoms. I've got atom A and atom B. Now, atom A could be 19 twice and 121. Atom B could be 19 twice and 121. Okay, 121. Right, now we just have to put them together. So that's going to be 38, 38, and 40. Is that correct? 19, yeah, 40. And then we're going to have 38, 38, and 40. Then we're going to have 40, 40, and 42. Right, so my ratios are 4-to-4-to-1. So I'm going to have a peak at 38 of height 4. So there was 2. So we need to double the height of that one. So that's going to have a height of 4, and it's going to be at 38. I'm then going to have another peak exactly the same height. Yeah, at 40 with a height of 4. And then I'm going to have a baby peak of 1 at 42. Clever game. And that would be So you'd actually, the 4 marks would be 2 marks for those guys being at their numbers in their correct ratios. This one is going to be 3 peaks and in their correct ratios. 4 marks in total. Clever games, these. And it is just a game. It's just a game show. And as I said, the Punnett square works really well for this. Right. Okay. Okay, right. So now that we've finished the diatomics, we can now talk about bigger molecules. So you can put a new title of molecular mass spec. Okay. So now molecular mass spec is actually the most commonly done mass spec in the world. They do it at airports every single day. They do it for drug testing, etc., etc. So what we're doing is, instead of putting in an element, oh, Mr. Duncan, how do you know that the 19 is repeated twice? Because for the bromine, none of the numbers were repeated, but for chlorine, both of them were repeated in the Punnett square because of the ratios. Yeah, it's because of the ratios, Aisha. So they told us that there was going to be 2 fluorine 19s. So A could occur twice as 19, but it could occur once as 21. Yeah, I can draw it out if you like. So the fluorines bonded together. If we call this atom A and atom B, this fluorine on the fluorine atom A could have been 19 in a 2 to or 21 in a ratio of 2 to 1. Yeah. And then the fluorine B could have been exactly the same. So I have to put the 3 options that are there in the Punnett square. Does that make sense? I hope that helps. Okay, so in molecular mass spec, what we're now going to do is, instead of putting in elements, we're going to put in compounds. So you guys all watch the TV shows. You see the police officer turns up to a crime scene and they find a bag of white powder. And what you see is, the police officer then, cuts it open, sticks his finger in it, gives it a taste and tells you what it is. That is not what is done today. He could be tasting cyanide, guys, and it'd kill him in a heartbeat. So you don't taste anything these days. Everything's done in these machines. So what we do is, let's choose someone simple. Let's choose someone like propane. That's a great example. We're going to take propane. So let's draw it out. C3H, double it and add 2, 8. So we're going to add propane. The great thing is propane's already a gas. Don't even need the vaporization chamber for this. Let's draw it out. I'm going to take propane. I'm going to add it. I'm going to input propane into the mass spec device. Now, when we put propane into the machine, we get a rather cool graph. M over Z and abundance. Okay, so here's what you get. First of all, and this is the only peak that you guys need at AS, but however, Edexcel and their infinite wisdom have actually asked about this at AS, which is rather annoying because they shouldn't, but they have. You're going to get a peak at 44. Now, the peak at 44 is the parent ion. It is the last big peak. Yeah? It's the parent. What that peak there is the entire molecule intact having lost an electron. Because the MR of propane is 44. 12 plus 12 plus 12 plus 1, 1, 1, 1, 1, 1, 1, 1 is 44. And the whole thing is positive. Don't forget your charge. So you see what's called the parent ion. Now, just to let you know, every now and again, you will see a tiny baby peak at 45. This is a baby peak at 45. Now, the reason for that is isotopes. Most commonly, carbon-13. Carbon-13 is relatively common. So you will get a tiny peak, but it's not the molecular ion peak. It is the parent ion peak. This peak here is the last big peak. And by the way, I often sometimes replace the word big with reasonable. The last reasonable peak. Because you can't call that a peak. That's pathetic. Guys, size matters. I don't care what anyone says. Size matters. And that is the last reasonably, this one here is the last reasonably sized peak. Yeah, that one's not a peak, it's pathetic. That's an isotope peak. That's a C13. That's a propane which has a C13 in it. Yeah. They often say, explain why there's a peak, a tiny peak at 45. And you go, because there were isotopes like carbon-13. Yeah, you make containers, all that jazz. Right, so what else are we going to see? Right, now we need to talk about fragmentation. Molecules like to break. So we now need to look at propane from its bonds. So the first thing is, what we could have is we could have a hydrogen break off. I'm going to try and color code this as best I can. Yeah, so we could have a we could break one of these bonds. Crack. Yeah, now these actually are very rare. If that happens, I'm going to form H+, so I'm going to detect that ion. I'm going to get a tiny peak at 1. That's created by H+. But what else would I have made? Would have been this, but neutral. Yeah, whenever you fragment a positive ion, that positive charge can only go with one person. And in this case, it's gone with the H. But it could have gone the other way round. And in fact, some of them will. Some of them will produce this. Some of them will produce that. Now, if that happens, I'm going to get a tiny peak at 33, at 43 as well. There you go. Now, that is a fragmentation peak of a hydrogen breaking off. These are very rare. Now, why are these rare? So this is a really important nota bene now, folks. Yeah, I need you guys to know this. Nota bene. Yeah, carbon-hydrogen bonds are very strong. You need to know this. Yeah, are very strong. What that means is even if you knock off an electron from one of those bonds, most of the time they'll still make it through the machine unbroken. They're that tough. Carbon-hydrogen bonds, well hard. However, carbon-carbon bonds, on the other hand, not so strong. So if I remove an electron from here, then it's going to fragment. And what would that now do? So if I'm going to redraw this again. So if I now redraw it, you can do the same thing if you like. So I'm now going to knock off an electron from the carbon-carbon bond. Yeah, I'm going to chop it here, and it's going to fragment. I'm going to have my electron hit one of those, and I'm going to crack it right down there. So what am I going to make? I'm going to make two things. I could make CH3 plus, and the plus would be on the C. Yeah, and the other half would be the rest of it uncharged. Yeah, the electron that was left went away with this guy. So there's the dot there is the electron left behind, and that's uncharged. And what I will see is a peak at 15. This is called a methyl peak. I'm going to get a peak at 15. And that's going to be caused by CH3 plus. Now, if that can split that way, what it can also do, or it could go the other way. The electron could go with the other guy in either direction, in which case I'm going to see this. Yeah, and I'm going to detect the other guy, because now the other guy's positive. It splits probably 50-50. So we're now going to see another peak, 44 minus 15, 29. We're also going to have another peak at 29. And that one will have been caused by CH3, CH2 plus. And at that point, that's the only graph you get. There are also little tails on either side of isotopes all over the place. Yeah, but we just ignore those because they're just baby peaks. So isotope peaks don't care. So it's a really fun game. So just to tell you, so at this point, people go, God, why do I even care? I'll show you why. Because carbon dioxide versus propane. Now, the reason why I'm saying we compare these is because the MR of carbon dioxide is 44.0. The MR of propane is 44.0. If you put these into a mass spec, you'd expect to get exactly the same peaks, and you'll get one peak that's the same. Yeah, you're going to get, what I'm going to do is let's do the carbon dioxide first in red. So this is M over Z, and this is abundance. I'm going to see a peak at 44. There's the parent ion, parent CO2 peak plus. Yeah. The next thing is I probably will see no other peaks because carbon dioxide is a double bond. If I break one of those bonds, yeah, then it's probably going to still make it through the machine anyway. It's still got an entire bond intact. Now, that's not always true. We may see some tiny fragments. We may see a tiny peak at 16 for oxygen. We may see a tiny peak for oxygen atom, and we may see one. So if we split it here, we're going to see 16 oxygen, O plus, that's this one, O plus at 16. But we're also going to possibly see that's one way to go, but it could also go the other way, O and CO plus. So we'd see the other guy, so minus 16 from 44, I'm going to see a peak at 28. I'm going to see a peak at 28. Yeah, and that's going to be CO plus. Nice. But they're going to be small peaks because double bonds don't tend to want to fragment. But in propane, what we realize is, let's change my color. Let's do propane in green. Propane, I get the same parent ion, so that's not going to help me. However, I'm suddenly realizing I don't really want to, I want to do it like, oh no, what's going on? It's doing weird things to me. There we go. So we're going to get the same parent peak. However, in propane, I'm going to see a peak, a big peak at 15. And that, of course, is CH3 plus. And I'm also going to see a big peak at 29 of CH2. So I can tell the difference in the mass specs of these because the peaks will be different. Does that make sense? It's really clever. Hi, sir. Oh, wait, wrong time. Nice one, Ryan. Good job. Yeah. So, guys, this brings us to the end of mass spec. So, fragmentation. It's nice to see parent peaks. You can use parent peaks. I'm tempted to look at some questions now at this stage. I'm not going to. I'm going to leave this today. You guys have a homework to do, so you can use the rest of the lesson to work on your homework. Guys, I set a homework on the classroom, which has some molecular ion peaks in it. So you can use the rest of today's lesson to have a look through that homework. I don't know how much time is left in this lesson. Not a lot, 5 minutes. So you guys can use the next 5 minutes to have a look at those questions and try and get your homework done, ready for next lesson, because I'm going to go through it. And guys, that brings us to the end of mass spec. So next lesson, we're moving on to electron configuration. I'll see you guys soon. See you later, guys.